Hello, everyone, and welcome back to our series on the theory and algorithms of knowledge tracing. Today, we're diving deep into one of the most fundamental and influential models in adaptive learning, BKT, or Bayesian knowledge tracing. By the end of this video, you'll not only understand the intuition behind BKT, but also be able to trace the calculations step by step. Let's get started. In this session, we have 5 key goals. First, we'll build a strong intuition for BKT using a real-world analogy. Then, we'll break down the 4 core parameters that define the model. Next, we'll walk through the algorithm's 2-step process. The highlight will be a full manual calculation example to see BKT in action. Finally, we'll answer the crucial question: where do these parameters come from? Let's begin with the intuition. So, what is BKT? Let's use a simple analogy. Think of it as a teacher holding a secret mastery meter for a student learning, say, linear equations. This meter shows the probability that the student truly understands the concept. But every time the student answers a question, the teacher updates this probability. The key idea is that the student's actual knowledge is a hidden state. We can't see it directly. We can only make educated guesses based on their observable performance. To make these updates mathematically precise, BKT relies on 4 core parameters. Think of them as the DNA of the model for each specific skill or knowledge component, like solving linear equations. First, L0, initial mastery, represents our best guess about a student's starting knowledge level. Second, T, transition/learning, is the learning rate, how likely a student is to learn the skill from a single practice opportunity. Third, G, guess, accounts for lucky guesses. Finally, S, slip, accounts for slips of the pen or momentary forgetfulness. Combined, these 4 probabilities allow BKT to act as a hidden Markov model, inferring the hidden state of student knowledge from their observed answers. First up is LLEA, the initial mastery probability. This is our starting point. It represents the probability that a student knows the concept right at the beginning before they've done any work on it. For a brand new topic, this is usually set low, maybe between 20% and 40%. If we set LO to 0.3, we're saying there's a 30% chance the student already understands linear equations. Next is T, the transition or learning probability. This is the chance that a student successfully learns the concept during a single practice attempt, but only if they didn't know it before. Learning is hard, so this value is typically low, around 10% to 30%. A t-value of 0.2 means there's a 20% probability that this specific problem will be the one that makes the concept click for the student. Third is G, the guess probability. This accounts for the times a student gets the answer right for the wrong reason. They guessed correctly. The value depends a lot on the question format. A multiple-choice question with 4 options might have a G of 0.25, while a fill-in-the-blank might be closer to 0.1. A G value of 0.1 means there's a 10% chance the student will get the answer right, even if they're completely clueless. Finally, we have S, the slip probability. This is the opposite of guessing. It's the chance that a student knows the correct answer but makes a mistake anyway. A careless error, a miscalculation, or a moment of brain freeze. This value is usually small, between 5% and 15%. An S value of 0.15 means there's a 15% chance the student will slip up and get the answer wrong, even though they understand the concept. Now that we have our 4 parameters, how do they work together? The BKT algorithm follows a simple 2-step cycle for every question a student answers. First, we perform an observation update. We take the student's current mastery probability and update it based on whether they got the question right or wrong. Then we perform a learning update. We account for the possibility that the student learned something from attempting the problem. This updated probability then becomes the starting point for the next question, and the cycle continues, refining our estimate of the student's knowledge state with every interaction. Let's meet our student Xiao Ming, who is learning how to solve linear equations. Our teacher has set the initial parameters. L is 0.3, T is 0.2, G is 0.1, and S is 0.15. We're going to walk through two questions and see exactly how Xiao Ming's mastery probability changes. We begin with question 1. Xiao Ming's initial mastery probability is 30%. He attempts the problem and gets it wrong. Now, let's perform the first step, the observation update. When a student answers incorrectly, we use this specific formula. The numerator represents the probability of not knowing the answer and not guessing correctly. The denominator normalizes this by adding the probability of knowing the answer but slipping up. Plugging in our numbers, the numerator is 0.7 times 0.9, which is 0.63. The denominator is 0.63 plus 0.045, which is 0.675. Dividing them gives us approximately 0.933. Wait, that's the probability he doesn't know it. So, the probability he does know it drops significantly to 1 minus 0.933, which is 0.067 or 6.7%. Now for the second step, the learning update. A common simplification in BKT is that if a student gets the answer wrong, we assume they didn't learn anything from that attempt. Therefore, we skip the learning up. The mastery probability going into the next question remains at 6.7%. Moving on to question 2. Xiao Ming's current mastery probability is 6.7%. This time, he attempts the problem and gets it right. Let's apply the update cycle again. For a correct answer, we use a different formula. The numerator is the probability of knowing the answer and not slipping up. The denominator adds the probability of not knowing but guessing correctly. Using our new prior of 0.067, the numerator is approximately 0.057. The denominator is approximately 0.150. Dividing them gives us a new mastery probability of about 0.379 or 37.9%. That's a big jump from 6.7%. Now for the learning update. Since he got it right, we assume he had a chance to learn. The formula adds the probability of learning to the current mastery. We take the 37.9% and add to it the chance he didn't know it, 62.1%, multiplied by the learning probability, 20%. This gives us 0.379 plus 0.1242 for a final mastery probability of 0.503 or 50.3%. So, after two questions, Xiao Ming's mastery probability has gone from 30% down to 6.7%, and finally up to 50.3%. You might be wondering, how do we get the values for LT, G, and South in the first place? Do we just guess them? Absolutely not. In practice, these parameters are automatically estimated from real student data using a powerful algorithm called the EM algorithm, or expectation maximization. Think of it as a super smart teacher who analyzes the past performance of thousands of students to learn the typical behavior of a particular knowledge component. The EM algorithm works in two alternating steps, repeated many times. In the E step, or expectation step, the algorithm uses its current best guess of the parameters to infer the hidden mastery states of all students for all questions. In the M step, or maximization step, it uses those inferred states to calculate new, improved parameters. This cycle repeats, getting better and better at estimating the parameters until they stabilize. It's a beautiful example of machine learning in action. So, to recap, BKT is a powerful and intuitive model that allows us to estimate a student's knowledge state in real time. It's the foundation of many adaptive learning systems. However, it's not perfect. It simplifies knowledge into a binary state and doesn't account for factors like question difficulty or multiple related skills. These limitations have led to the development of more advanced models, which we will explore in future videos. Thank you for watching. I hope this step-by-step guide has demystified Bayesian knowledge tracing for you. If you have any questions, please leave them in the comments below. And be sure to subscribe, because next time we'll build on this foundation and explore some of the more modern and powerful knowledge tracing models that are pushing the boundaries of adaptive learning. See you then.